All right, in this example, we're given the graph of a function y equals f of x. And what we're going to do is we're going to go through and identify all the intervals where our function's increasing or decreasing, all the intervals where it's concave up, concave down, and then we're going to identify all the interesting points: local max, local min, absolute max, absolute min, and inflection point. All right, so let's start with the local max and local min. This is going to influence our intervals for increase, decrease. All right, so first of all, when we look at this graph, local max, it's a high point. Just along our curve, it's a high point. And we see one right here, right at x equals 3. And then we also see a local minimum right here at x equals 5. So we have a local max. The value is, what is this point? The y value is 5. So the local max value is 5, and it occurs at x equals 3. All right, so that's our local max. Our local min occurs at x equals 5, and the value looks to be, we're kind of estimating here, maybe like 3.7. And it occurs at x equals 5. So we have a local max at x equals 3, and we have a local min at x equals 5. All right, so let's keep that in mind. And what these local maxes and local mins are doing here is they kind of split up our interval, or split up the sections of our graph where our graph is increasing and decreasing. So if we're looking at this, in this section over here, if we look to the left of this local max, what's happening? Well, our graph looks to be increasing. So as we read from left to right, the graph is going up. So over here, it looks like our graph is increasing. In between these two, the local max and local min, what does it look like our graph's doing? Well, it looks like it's falling. It's decreasing. So it looks like it's decreasing in here. And then if we go to the right of our local min, we read from left to right, it looks like our graph is going up and up and up. And let me squeeze this in. So it looks like we're increasing over here. And actually I'll put the arrow there we go. Yeah. So notice that these local extremum, the max and the local min, kind of split up where our graph is increasing versus where it's decreasing versus where it's increasing again. So our graph here is increasing on the interval, and again, the graph just kind of trails off over here, and it trails off over here. So without any further information, we just assume that the trend kind of continues, and our function's just defined for everything here. So we would say our intervals for increase are from -infinity to 3 and from 5 to infinity. And then our intervals for decrease are in between 3 and 5. Okay. So that gives us a pretty kind of good picture of what our function's doing. But now we can also investigate, well, what is the shape of our graph? And so when we look at this, if we're talking about the shape of our graph, right in here, it's clear this is concave down. So right in here, we have that concave down sort of frowning shape. So it's clear. Right in there, we're concave down. And then over in here, we have that concave up kind of cup shape. So over in here, we're concave up. And when we change shape, when our continuous function changes shape, it changes shape at a specific point. So it's kind of, inflection points are kind of hard to determine where they occur exactly just by looking at it. So it's easy to kind of point out, all right, here's a local min and local max. Inflection points are a little more subtle. They're a little harder to see. But it helps to identify the regions. So here's a region concave down. Over here, here's a region concave up. And the inflection point has to happen somewhere in the middle. So maybe right around here. So I'm thinking this is our inflection point. And to the left of that inflection point, our graph has that concave down shape. And a lot of times I abbreviate concave down CD. You could also use CCD. That's another common abbreviation. And concave up CU or CCU. And then on the right side over here, we're concave up. And you could check the concavity at any of these points by just kind of visualizing. Let's draw in a tangent line. So if I were to draw a tangent line in here, I can see that the graph, here's my tangent line, and then the graph kind of bends above that tangent line. Or maybe over here, if I were to draw in a tangent line, what's happening is the graph kind of bends below the tangent line, so it's concave down. So what we've found here is our graph looks to be concave down on this section of graph, everything up through our inflection point, which happens at x equals 4. So we're concave down on the interval from -infinity to 4. And then at that inflection point, which happens at x equals 4, our graph becomes concave up. So we're concave up on the interval from 4 to infinity. And our inflection point happens at x equals 4. So that's where we change shape. All right, what about absolute max and absolute min? Well, this graph doesn't have any. Doesn't have an absolute max. So yeah, this point here is a local max. And for this whole section, it's the highest point. For this whole section, it's the highest point. But then we have this little section of our graph right here. And this keeps going. So it keeps going up and up and up. So no matter where we kind of pick a point, so if I were to say this is my absolute max, well, I could find a point that's slightly bigger. And if I think that point's my absolute max, well, I could go higher. And so we could kind of keep working our way up. And so there's a whole bunch of points here that are just kind of being one-upped as we go. So there is no absolute max. And same thing for absolute min. Yeah, this is a local min, but eventually if we read far enough to the left, we hit a place where then our graph just keeps getting lower and lower. And no matter where we pick on here, if I think this is my absolute min, I can always find a point that's lower. If I think that's my absolute min, I can still find a point that's lower. And I can always just keep going down. And so there's no absolute min on this graph. All right. So that's a good example, just given the graph of a function, being able to pick out all of this nice information, all these nice definitions that we've been talking about.